So good afternoon, everyone. This is the introduction. I'm Giordana Bucchioni, and I'm a postdoc in between the Department of Information Engineering, in particular the Laboratory of Robotics, Autonomous Automation and Autonomous Systems, and the Department of Mathematics. And this mix is actually also the idea behind my research, because I'm trying with some effort to take some advantage from the knowledge of the dynamics of the restricted frequency problem to propose innovative solutions to increase the autonomy of. And this is also a kind of the idea behind this preliminary study for transfer between her. So in the next years, there will be this going on. It's not a far future. There will be an increasement of number of missions to the moon. The gateway is one of these, but this is just an example. And not only the American and European sides will bring a spacecraft in the proximity of the moon, like a spacecraft will stay there, but also the Chinese, the Indians. So it's becoming like a hot topic. And today, this spacecraft, this station, will need to be refurbished. And so it will be necessary to have a continuous interchange between the Earth and the moon to bring actually stuff to bring on the orbiting space station. And the idea of today is to use resonance orbit plus manifolds plus Lambert-Arcs to continuously connect a station that is orbiting in the proximity of the moon and the Earth. The working framework for you is well known, because I work in the circular restricted frequency problem that for a preliminary design is very useful and is very common in the literature. And I work in the synodic reference frame, so a rotating reference frame between the Earth and the moon. My working framework is an example is, as I was saying, the orbit of the gateway. So we have a 9-2 resonance orbit and a near elliptical orbit around the point, Lagrangian point L2, with the characteristics that you can see here. All the results are got numerical methods. And for me, I will for this work, I will evaluate the goodness of the strategy in terms of fuel consumption, so delta V consumption, and time of flight. I want to save fuel to go back and forth more, and I want to go back and forth as fast as possible. The idea is to find a resonant periodic orbit that connects the Earth and the proximity of the moon. Then to introduce an intermediate parking orbit to exploit the dynamics of the manifold of this intermediate parking orbit, because as you may know, the NRHO is a very stable orbit. So the manifold evolved very slow. And for this kind of practical application, slow manifold takes a lot of time. And we don't want, as I was saying before, we don't want to have very large waiting time or time of flight. So yes, this is what I was saying. This is the Earth. We have an intermediate parking orbit, and we have the target orbit. That is the one that we want to reach periodically. Then this is a first solution approach using only manifold to connect this periodic orbit, the resonant periodic orbit, and the target orbit. Another solution, instead, to gain time, is to connect the parking orbit and is to connect the arrival orbit and the resonant orbit with Lambert-Arcs, but not in the two-body problem, in the standard formulation of the Lambert problem, but with some numerical correction that I will explain later. So this is just an intuitive way to give you an idea of what is the goal of the work. So I have a spacecraft that is located on a resonant Earth-Moon orbit. It will go in the proximity of an intermediate halo orbit that is I'm anticipating it is an halo orbit around the Lagrangian point L1. Then it will transfer to the near rectilinear halo orbit. And once the rendezvous and docking and the transfer of material is done, the spacecraft must return to the intermediate orbit and then to the resonant orbit. This is the goal of the study. So the first step was actually to look for a proper resonant orbit. Here there are the first study. I forgot to understand. The first step was to look for a resonant orbit in the two-body problem. So considering only the Earth as its main body, but the influence of the Moon is not negligible. And so the following step was to perform some numerical differential correction, knowing some symmetry, taking advantage of the symmetry of the proposed resonant orbits, and that's the differential correction procedure, to get the orbits in the circular restricted three-body problem framework. So these are three proposed resonant orbits for the back and forth from the Moon and from the Moon to the Earth and the other way around. The next step was to look for a proper parking orbit. So as I was saying before, we are looking for an orbit that is not super stable because we want to exploit the dynamic of stable and unstable manifolds to reach the intermediate orbit and then to reach the final orbit. So we numerically attempted to find to compute a different intermediate halo orbit around the Lagrangian point L1, and then we numerically computed the delta V that was necessary to go from the parking orbit with unstable manifold to the NRHO and back. And as you can see here, the most convenient one is the green one. That is defined by these parameters. Then we investigated also the possibility of using manifold of the parking orbit to connect with the resonant orbit for the back and forth and to save some delta V. And we were able to find some intersection. Everything is still done numerically. That lead us to the selection of one particular parking orbit. So, as you can see in this graph here, we considered only the intersection between stable manifold of the parking orbit to leave the resonant orbit, reach the intermediate parking orbit, and then move to an unstable manifold and go to the NRHO, and then do the path all the way back. I will show you a quick video to be more clear. But among all these trajectories that we found, we consider only the one that had a period, time of flight, that was a multiple of the period of the target orbit. This is because in this way, we can intercept the spacecraft that is orbiting on the NRHO every time. So we basically, we are on the resonant orbit, we leave the resonant orbit, we go in the proximity of the intermediate orbit, then we reach the NRHO, we are sure that we can find the target there, and then we leave the NRHO, and then again. In fact, the orbit that was selected is the 3-1 resonant orbit, because it's the one that allows us to spend less delta V and also to save some time. So time is 100 days. That's for engineering point of view, it's a lot, but it's not bad. Okay, so this is the video I was talking about. So this is basically an example of trajectory. We have the spacecraft that is orbiting on the resonant orbit. Then it will leave the orbit. It exploits manifold of the intermediate orbit that you see here. It reaches the NRHO, and then it stays on the NRHO for a little while. Then it leaves. It intersects another manifold, and it is able to get back one point on the resonant orbit. And this is an example, but as I was saying before, 100 days can be too much. So we also investigated a way to save some time, exploiting this idea of Lambert-Arcs. So the Lambert theorem is usually used in the two-body problem to find an ellipse or an orbit that passes by 2 points. The idea here is to use the moon as main body to find the minimum energy ellipse that passes from 2 points in a determined time of flight, and then to use a numerical method that is basically just a single shooting to correct this initial guess. And here you can find, this is just an example of what you get with this Lambert-Arcs procedure. Here we compared the two methods. So manifolds, only manifolds to leave the target orbit, get to the target orbit and back, or only Lambert-Arcs. And as expected, with the Lambert-Arcs, you spend way more energy. So the delta V for me is kilometer per second, quite a lot. And you save a lot of time. So from 120 days, you move to 40 days. So we decided to try to combine these two methods to reduce the energy consumption and to find a compromise on the time of flight. This is the problem we all have. We want to go somewhere, we want to go there fast, but we want to spend not that much. And these are the results. With this combination, we are able to reduce the time of flight. We are around 80 days, but we are able also to reduce the delta V consumption. And we found out that the best combination is to have a manifold to reach the target orbit, so to exploit the stability of the intermediate orbit, and then to have Lambert-Arcs to leave from the target orbit. Okay, so this is just a numerical example of the results. In here, we spend 2.43 kilometers per second, and we have 40 days. This one, we spend a bit more. This is only manifold, and it's not very convenient in terms of time. And this is the best solution that I was saying is a combination between manifold and Lambert-Arcs. So the idea was to propose a preliminary study, because in the SQL restricted two-body problem is just the beginning, then we have to step for validation of the results, to continuously commute in the future between the Earth and the Moon. And we proposed 3 different approaches based on the partially based on the stability and stability properties of the non-Kepler orbits that we have in the Earth-Moon restricted three-body problem. And we found out that the best solution was a combination between natural dynamics, natural stability, and a kind of brute force approach that is the Lambert-Arcs. In the future, as I was saying, it will be important to validate this approach, also to move to more complex model, to insert the dependency of the date of this approach. And it would be also important to study how much does it cost for launch something that must be launched from Earth to reach the resonant orbit. Okay, thank you. And I forgot to say that this work was done in collaboration with Professor Innocenti, Tommaso Donati, and Giordana Bucchioni. So it was.